Good morning, everyone. I am Massimiliano Marino. I am a PhD student from the University of Catania, Italy. And part of my PhD project is about wave current interaction at the right angle over rough beds, with a particular focus on boundary layer. Waves and currents are usually simultaneously present in coastal waters. Their combined flow plays a fundamental role in several coastal phenomena such as sediment transport, mixing processes, diffusion, and others. Their interaction usually occurs with the near orthogonal angle in the coastal environment. However, most of the combined flow theoretical models have been validated with collinear interaction experiments, which means with waves and current propagating in the same or the opposite direction. Recent studies show an insensitivity of some of these models to the angle of attack between waves and currents, which may lead to an under or an overestimation of important flow dynamics quantities such as shear velocities or equivalent roughness. This is probably due to a lack of experimental data of wave-current orthogonal interaction, probably related to the difficulties of the physical modeling. So the objectives of this work are to provide a new dataset on wave current orthogonal interaction over both smooth and rough beds, with a particular focus on the shear effects due to the superposition of the waves on the steady current, and investigate the turbulence into the boundary layer. This has been achieved with an experimental investigation in a wave current basin in order to study the mean and turbulent properties of the combined flow field and operate in the end a comparison with some analytical models. An experimental campaign has been carried out in a shallow water basin at DHI Denmark within a NIDAL plus T Transnational Access project. In the video you can see the wave maker in action in the basin and in the right and part of the experimental setup. The shallow water basin is 35 meters long in the current direction, 25 in the wave direction, and 1 meter deep. It is provided with current recirculation systems, which allows the generation of a steady current with a constant discharge of 1 cubic meter per second. It is also provided with a wave maker, which allows the generation of regular and irregular waves. And two series of panels have been positioned in the wave current interaction area in order to reproduce two different roughnesses. A first series with fixed grains of sand on top, and a second one with gravel. An array of 24 wave gauges have been positioned all over the measurement area in order to measure wave height and water level. And into a specific spot of the measurement area, 5 acoustic Doppler velocimeters have been positioned in order to measure velocities and reconstruct velocity profiles. A total of 18 runs have been carried out, 9 of which over sand bed and 9 over gravel bed. 3 wave current conditions have been performed, current only, wave only, and wave plus current. And a series, let's say, a range of wave conditions in terms of different wave height and period have been conducted. From the velocity measurement, a series of other quantities have been computed, such as free stream velocities, wave orbital velocities, and their relative Reynolds numbers. A wave field preliminary investigation has been conducted in order to assess the time and space variability of the wave height time series. On the left, you can see in yellow the phase average wave superposed on the wave height time series of a wave-only test. And just to give you some context, on the right, you can see our experiments denoted by the markers in the context of the wave theory's validity. So basically, we have generated in weakly nonlinear intermediate water waves between Stokes second and fifth order. Let me now show you the results for the mean flow analysis. On the left, you can see the velocity profile for the current only over sand bed test. The markers indicate the time averaged velocities, whereas the black line indicates the double averaged velocity profile, which means time and space averaged for all the velocimeters. On the right, you can see the same double averaged velocity profile, but in wall units, superposed on the logarithmic law and on the Van Dries theoretical profile. As you can see, the logarithmic profile, which is denoted by the gray circles, align satisfactorily with the theoretical profile, which means that the boundary layer is fully developed. This slide is analogous to the previous one, but over gravel bed. You can see a decrease of velocity at the bottom due to the presence of the rough bed and the corresponding increase of free stream velocity in comparison with the previous case. And on the right, you can see the same velocity profile aligned with the theoretical profile of Van Drießt. Let me now show you a comparison between current only and waves plus current velocity profiles over sand bed on the left and over gravel bed on the right. What we observed is that the superposition of waves always induces an increase of shear experienced by the current, which is shown by the increase in the shear velocity and in the apparent roughness. This result is basically in agreement with most of the studies, such as Kemp and Simons, Grant and Madsen, and others. However, this shear increase seems to occur in a nonlinear fashion. Figure shows the ratio between the combined flow to the current-only friction Reynolds number, which is an indicator of the relative shear increase determined by the superposition of waves, plotted against the wave current parameter UW to UC, which is an indicator of the relative importance of the waves compared to the current. So, as the wave current parameter increases, we can recognize three regions. First region on the left, where the current dominates, in which a shear gradient is observed as orbital velocity increases. A second region in between, in which the shear seems to follow a constant pattern, and the third region where the wave dominates, in which shear seems to increase again. And it's interesting how such trend is observed regardless of the rough characteristics of the pattern. Such a behavior has never been observed in my knowledge, but it recalls a work by Lodel et al., in which a constant pattern is observed as well, and then as the wave Reynolds number increases, the oscillatory flow induces a progressive increase of shear. However, in our case, there are some differences. First of all, in the study by Lodel, in the constant region, no increase of shear is observed. Whereas in our case, we always observe an increase in bottom friction when waves are superposed on the current. Moreover, when the current dominates, we observe a friction gradient, which is never observed by Lodel. However, we must consider that the ones by Lodel are very different experiments carried out in an oscillating water tunnel, thus without any surface effect, with collinear waves and currents, so we must take that into account. The present panel shows a comparison between the experimental velocity profiles and the selection of analytical models, the Grant and Madsen continental shelf model, an empirical formulation by Soulsby, and an eddy viscosity model by Stiles et al. The best performance is always returned by the Grant and Madsen model, which velocity profile estimation deviates from the experimental data up to 5%, whereas the Soulsby experimental formula usually underestimates the profile up to 15%, and the Stiles et al. Eddy viscosity usually underestimates the velocity profile over the sand bed and overestimates over gravel bed up to the 20%. Let's move on to the turbulent flow analysis. What you see here is a comparison between the current-only circles and the waves plus current triangles and diamonds of Reynolds stress profiles over sand bed on the left and over gravel bed on the right. The figures show that in the superposition of waves always determine an enhancement of the turbulence production at the bottom, and in some way confirms what we seen in the mean flow analysis. It has been observed that most of the turbulent kinetic energy transport in a current steady flow occurred during the succession of two events called ejections and sweep. Quadrant analysis is a technique which, at least in my knowledge, has never been used in the study of wave current orthogonal interaction, that allows to study these ejection and sweeps events starting from the turbulent velocity time series. On the right, you can see a schematization of the quadrant analysis. On the x-axis, there is turbulent velocity in the current direction, and the y-axis turbulent velocities in the vertical direction. And ejections and sweeps are associated with quadrants Q2 and Q4, so basically when the two turbulent velocities have opposite sign. This is an example of quadrant analysis. The numbers in light blue in each quadrant indicate the relative number of events that falls into each quadrant. But not all the events in quadrant Q2 and Q4 will be considered rejections or sweeps, but only the ones that are above a certain threshold called hyperbolic threshold, and this threshold is proportional to the Reynolds stresses and is shown in the graph by the hyperboles in red. In this panel, you can see the current-only quadrant analysis over sand bed on the left and over gravel bed on the right. If you look at the number of relative events in quadrant Q2 and Q4, you can see that from the sand bed and gravel bed, there is not huge difference. This seems to suggest that in presence of a rough bottom, the turbulence enhancement is not due to an increase of the number of ejections, but rather an increase of their intensity. Instead, in the waves plus current case, in comparison with the current-only case, we notice a decrease of the relative number of the ejections and sweeps events. But we know from the Reynolds stresses that the superposition of wave operates a turbulence enhancement at the bottom. It is possible that in a certain part of the phase of the wave, the ejections and sweeps of the current may be suppressed, while in other parts of the phase of the wave they may be enhanced, because in the overall we have a turbulence enhancement. However, in order to say that for sure, we should carry out a phase averaged quadrant analysis, which is under development at the moment. So in conclusion, the presence of waves always determines an enhancement of shear, which is shown by the increase of the friction velocity and the equivalent roughness. And let's say a non-monotonous relation has been observed between the shear experienced by the current and the wave current parameter UW to UC. And between all the models that we have compared, the Granden-Madsen model showed the best performance in predicting the velocity profiles and the shear velocity. The Reynolds stresses confirmed what we have seen in the mean flow analysis, while the quadrant analysis showed that the superposition of the oscillatory flow induced a decrease of turbulent ejections and sweeps, but an increase in their intensity. But this for sure require further studies. Thanks for your attention.